Let's start with questions. Do you have any questions? Any questions? So again, at the end of the hour, right? I mean, I could ask you about sequences. I could ask you about some of the beginning parts of series, including geometric and telescoping. But I'm not going to ask you anything about sort of the things we've been talking about the last couple of days, at least, right? Last time we talked about alternating series test. And one thing, and we're going to continue to talk about alternating series test, and in particular, some of the specifics surrounding the alternating series test and some of the strange things that come out of alternating series. This is, like I said, this is the first time that we've really talked at any length about series that have both positive and negative terms, okay? The way the book sets up alternating series, a little bit strange. They give two forms for an alternating series that either begin or end with a negative number. And they basically assume that the AN part is still positive and that the sign is coming from just the -1 to n or n+1, if you will. And the alternating series test simply provides a couple of conditions that guarantee convergence of an alternating series. Yeah? And the two conditions are basically stated succinctly that the terms have to, right, the terms ignoring the pluses and minuses, the terms have to decrease, yeah? And they have to decrease where? To 0, yeah? Now the first that last stipulation, namely that the terms have to go to 0, which is the, the first requirement right there, that was necessary to even have convergence anyways, yes? But there's one additional stipulation that guarantees convergence of an alternating series, and that is that the terms don't just decrease or don't just go to 0, but they do so in a decreasing way. And if the terms decrease to 0, you are guaranteed to have a converging alternating series, okay? Now, does that mean that if an alternating series doesn't have terms decreasing to 0, if like the terms go to 0, but they do so in some other way, does that mean that that series will automatically diverge? No. Okay? It just means the alternating series test failed to tell us whether the series converged or diverged. It may still happen that you'll have an alternating series that fails the alternating series test, and the terms do go to 0, but not in a decreasing way, and you will still have a converging series. But this is just one way to know for certain that you have a converging series on your hands. And by the way, does the alternating series test tell us what the series converges to? No. Yet again, we have a test that does not tell us what the series converges to necessarily, yeah? So again, let's sort of talk through the tests that we have, okay? So this is just a good exercise to do on your own. First of all, convergence of a series means convergence of the sequence of partial sums, okay? So that's why we talk about sequences and series at the same time, because convergence of a series means convergence of a very particular sequence, namely the sequence of partial sums. Okay, so we use that fact to really get at geometric series and try to understand them well. And we completely characterized geometric series. We said when they diverge, and we said when they converge, and what they converge to, even in that case, yeah? And then we also use that definition about partial sums to deal with so-called telescoping series, yeah? And that involved partial fraction decomposition as well, okay? So geometric series, telescoping series, then we had the so-called nth term test, which said, and by the way, the nth term test also came from the sequence of partial sums. And essentially the nth term test says what? What does the nth term test say? No. Okay, so if a series is going to converge at all, what has to be true about its terms? The terms have to go to 0. Does that make sense? If a series is going to have a chance to converge, you guys ever seen the movie Dumb and Dumber? Okay, look, I'm not sort of advocating that that you go watch that or anything, but there's sort of a critical part where, you know, Jim Carrey is saying, yeah, you know, he's like in love with this girl or something, right? He's like, look, I just want you to level with me. What are my chances here? And you know, like 1 out of 100. What are my chances? And she's like, well, more like, you know, 1 out of 1,000,000. And he goes, you know, so you're telling me, right, there's a chance, right? I mean, I get it. I hear you. I hear what you're saying. Okay. So I want you to sort of think somewhat along those lines when it comes to the nth term test. In order for there to be a chance to converge, what has to be true about the terms themselves? They have to go to 0. Then you at least have a chance of converging. Does that guarantee that the series will converge? No. Therefore, if the terms aren't going to 0, what do you know already? Series diverges. Yeah? Okay? So if the terms go to 0, what you say to yourself is, okay, so you're telling me there's a chance that the series might converge, yes? But it's not telling you that the series does converge. I wish it did, but it doesn't. Okay? And what is the kind of quintessential example of a series whose terms go to 0 and yet diverges nonetheless? The harmonic series, okay? I'm just sort of talking through the sort of things that we've been talking about together, okay? Then we moved on to the so-called integral test, okay? And in the integral test, we said, okay, if a series consists of terms which are positive and decreasing to 0, then instead of looking at the series, I could basically look at the integral with like n replaced by x, and, you know, n going from 1 to infinity, or n going from wherever to infinity, with x going from wherever to infinity. And if the improper integral converges, the series converges. And if the improper integral diverges, the series diverges, yes? And we talked about geometrically why that works. Then we use the integral test to tell us something specific about certain kinds of series. The p-series, yes? We talked about when a p-series converges. A p-series, which is like sum 1 over n to the p, that thing will converge precisely if p is bigger than 1 and it diverges otherwise, yes? Okay? The integral test told us that. The integral test also told us stuff about another, you know, I kind of threw this one in for free, the logarithmic p-series situation, yes? Where you basically put a logarithm in the numerator. I don't care what power you raise the logarithm to, the condition is exactly the same there. So it's like logarithm to some power over n to the p. That series will converge precisely if p is bigger than 1, just like it did in the case of the ordinary p-series. Okay? All right, so integral test. Then we went to what? Direct and limit comparison, yeah? And then the direct comparison test, these were still series of positive terms, technically, especially in the direct comparison case. If you're able to slip a diverging series underneath, a series you know to diverge, underneath a series that you're trying to figure something out about, then of course, since the diverging series is smaller, it would force the other one to diverge, yes? By the same token, if I'm able to slip a converging series above the series in question, then the series in question has to converge, yeah? And then limit comparison, basically that just allows us to boil the fat out of the terms. We say, look, there's a bunch of junk in these terms that doesn't really matter in the end. Basically it's the n squared and the n cubed are like the leading terms of these rational functions. And the limit comparison test allows you to basically ignore parts of a term that aren't contributing very much and just focus on the meat of the matter. And most of the time, when you do that, you can actually make a conclusion fairly quickly, yeah? And I mentioned Stirling's approximation, right? Stirling's approximation is something I will allow you to use if you want, but I'm not going to force you to memorize that, okay? And then yesterday, we finally got to alternating series. And we looked at several examples, and that's where we stand right now. So that's just a review. Look, I've taught this class enough times. I just know it's good to sort of go back and like just go back through it again and again and again and remind yourself what it is that we're talking about. It also helps you develop kind of a language around these topics. Okay? Any questions before we move on? Any questions? All right. And by the way, just to let you know, we are like exactly on schedule. If you go and you like look at the schedule on the syllabus, I mean, we are literally like to the day precisely on the schedule, okay? So you can basically take that thing to the bank at this point. If it says there's going to be an exam someday, that's going to happen, okay? We're right on the exact day and the exact topic, everything. So that's a blessing for sure. I talked to you about, going and perhaps watching this video. It's kind of cool. It talks about sort of a natural reason for why we call the harmonic series, okay? But I want to talk about absolute convergence. Absolute convergence. Wow, that sounds amazing, right? Okay. Absolute convergence is, look, you basically take the absolute value of the terms, and if the series of terms in absolute value converges, and by the way, notice, do I have any -1 to the n's in here this time around? No, the -1 to the n's are gone. At this point, everyone, I'm just sort of abandoning what the book did. The book like tried to always make an positive, okay? And like have this alternation here. At this point, we're just saying, look, the terms might be negative. Does that make sense? The ands themselves, the terms themselves might be negative. And it might not necessarily be every other term. It might be like a couple of terms are negative, and then like 5 are positive, and then like another one's negative or something. But is this statement that I have right here, does it seem reasonable to you? If the series of terms where I take the absolute value of every term, if that converges, don't you think it's reasonable that the series of just the ordinary series without absolute value, that would converge also? Because if I go to just the ordinary series, I'm taking some terms that were negative turned into positives, and now I'm letting them be what? Letting them be negative again, yes? So in some sense, you're almost in a better situation than you were when you just took the absolute value of everything. Do you see what I'm saying? Like I have a series where some terms are positive, some terms are negative. I take the absolute value of every term so that everything just gets bigger. Excuse me, yeah? And then what I do is I say, oh, hey, even that series converges. Therefore, if I take the absolute values away, that series will converge, yes? I'm simply flipping the switch from the negative terms, making them all positive, looking at that, saying, hey, that's a converging series. Therefore, if I let the negatives come back, it's still going to be a converging series. Am I making sense here? Okay. That's called absolute convergence of a series. Yes? Okay, so the series 1 over n. Mm-hmm. That is connected to this, but that is not an example of absolute convergence. If you take the alternating harmonic series and you take the absolute value of every term, look, and look, you see I have this sort of admonition here at the bottom, right? So is the converse true? If a series converges, does the series in absolute value converge? And the answer to that question is no, and it's because of this example that you're bringing up. Okay, let me write it. So sum, okay, n going from 1 to infinity, -1 to the n over n, yes? Okay, and in this particular case, I'm thinking of this thing right here as being my an. Now, does that series converge? The alternating harmonic series? Yes, it converges by the alternating series test. This thing converges, but what? Series n going from 1 to infinity, absolute value of an, which is just this, which is just the harmonic series, right? But this diverges. So that's what I'm saying is the converse true? That means, can I go in the reverse direction? Am I allowed to go in the reverse direction? So series absolute value converges implies the original series converges. But is it true that if the original series converges, right? Is it true that if the original series converges, that the series of absolute value terms converges? No. No, it's not. Because, like, for instance, the alternating harmonic series converges by itself, but then when I take the absolute value of the terms, what do I end up with? The harmonic series which diverges, yeah? Okay, so you can only go in the forward direction with this, okay? So that's good to go, but in the backward direction, you better not do that, yeah? If the absolute value series converges, then you can conclude that the original series without absolute values will also converge. And you call such a series that converges in absolute value an absolutely convergent series. It absolutely converges. Because even when I slap absolute values around the terms, it still converges. Does that make sense? Okay, yes, Daniel. Yeah. Yeah.
So is the same reason that the non-absolute value series, the original converges, is that the same reason that like the converging, if you put a converging series above a series that you're in question, that like through comparison is, and then that series that you're comparing with,
It's sort of, but I mean, yeah, sort of, like for the absolute value thing, yes. But then, of course, we have to think about, well, but then what happens when some of the terms become negative? What this is saying is the terms are basically going to zero fast enough that even if I put absolute values around everything, the thing still converges. So since the terms are going to zero fast enough, clearly if I throw some negatives in there, the thing is still going to converge. Does that make sense? Like the problem, namely the terms not going to zero fast enough, is not the case here. Like even in absolute, like the terms are going to zero fast enough that even if I put positives on everything, the thing still converges. That's the essence of what's happening. Now, what about this? Okay, so the alternating harmonic series, let me just write this in here. The alternating harmonic series is not absolutely convergent. Not absolutely convergent, okay? But what about this series? Let me write another series up here, okay? So what about this? Sum n going from 1 to infinity minus 1 to the n over n squared. What about that? And again, here, I'm sort of, again, rolling the minus 1 to the n into my term now, yes? Okay? So what about that series? Well, what do you guys think? It converges absolutely. Why? Okay, so let's just, right, so if I take the absolute value, the series of absolute value of terms, that just gets rid of the minus 1 to the n. Do you know what I'm saying? So this is going to be n going from 1 to infinity, 1 over n squared, which converges. Why does it converge? Yeah, so it's a p series situation with p equal to 2. So what does that tell us about this series back here, just to be clear? What do we call this thing? It is absolutely this thing absolutely converges, okay? And the terminology is well chosen, is it not? Because you're talking about absolute values, yeah? So absolutely convergent means even if I slap absolute values around the terms, I still get a converging series. Does that make sense? Hopefully? Okay. Any questions on that? So here it is. Definition of absolute and conditional convergence. The series AN is absolutely convergent when the series of absolute value of terms converges. That's basically what we just said, yes? What do we call the things that don't do that? What's an example of something that doesn't do that? The alternating harmonic series, okay? The alternating harmonic series, what do I call that? Well, you call those conditionally convergent. Okay, you use this language, conditionally convergent. So basically what you want to think of is their convergence is conditioned on letting the negative things do their work and contribute appropriately. Does that make sense? So even the terminology there makes sense. Like the series will converge, but the minute you start getting rid of minus signs, the series diverges. Does that make sense? That's what a conditionally convergent series is. So an example of a conditionally convergent series, we already saw one. Sum n going from 1 to infinity minus 1 to the n over n. That thing converges on its own, but the series of terms of absolute values, that diverges, yeah? Absolutely convergent, we just saw an example of that, right? That was sum n going from 1 to infinity minus 1 to the n over n squared, for instance, right? You could probably think of lots of other examples, but that's one of them. Can you think of another example of an absolutely convergent series? I mean, don't think too hard, but can you think of another example of an absolutely convergent series? Right. Or I could, I don't have to have negative terms, do I? So I could just have, 1 over n to the 5th or something, right? That would work. Can you guys think of another conditionally convergent series other than the alternating harmonic? By the way, let me just ask you a question. A conditionally convergent series will definitely have negative terms in it. Does that make sense? Is that right? Because how on earth would you have both these things happening at the same time? Where the original series converges, but then I slap absolute values around and suddenly it diverges. Does that make sense? So a conditionally convergent series will have negative terms in it. Yeah? Yeah? You just say this thing will have negative terms. Okay? Conditionally convergent series will have negative terms. Okay? So give me another example. Look, I'm going to go ahead and slap in the minus 1 to the n because we know we probably are going to need something like that. Yeah? Can you think of another example of something that might work? Yeah, Daniel? Yeah, that would work. Natural log of n over n, yeah. Okay, that's natural log of n over n, that's going to eventually decrease to 0. Yeah? So by the alternating series test, this thing converges, and yet when you get rid of the alternation, you end up with something that is diverging. Yes? Sum log n over n, that's a diverging series. Because it's a logarithmic p series with p equal to 1. Yeah? Okay. Good. How about another example? Jared, you had your hand up. Did you have one? Yeah, like minus 1 to the n over the square root of n. That would work. Because that's like n to the 1/2. Clearly 1 over the square root of n decreases to 0. Therefore, by the alternating series test, this alternating series converges. And yet, when I get rid of the alternation, I end up with a series of positive terms where it's a p series with p equal to what? 1/2, which is a diverging series. Make sense? Okay. Okay, so all of these guys are conditionally convergent series. Yeah, yes. Well, yes. Yeah. So, I mean, there's some really interesting ones. Like, for instance, the series of like sine. Okay. Like 1 over, like sine n over n or something like that. Pretty sure that you can show that that's actually a converging series. Sine n, where the trigonometric function sine n over n. Now, you might say to yourself, what? You know, what's going on here? Well, sine n, sine of n, that's going to be negative sometimes and positive other times. Does that make sense? And it turns out, I mean, I would have to go look at this again, but I think it's negative just enough that it actually caught, because, I mean, do you see a comparison between that and like maybe the harmonic series? Because what's the maximum that sine n could ever be? 1, right? So you might suspect offhandedly that that series would diverge, but I think it actually converges, okay? But when you take the absolute value of the terms, you get a diverging thing, okay? So that's a good question. Other questions?
I guess that's a follow-up question. Is there, so to have like a conditional convergence rate, you have to have some part of the function that alternates sine or negative one. Like that sort of thing where it goes over and back.
Well, there needs to be some kind of cancellation that happens between positive and negative terms. And it needs to happen in such a way that it causes the series to converge. Then when you take the absolute value of the terms, you know, you realize that that cancellation was really important. That if everything were just positive, you're suddenly in trouble. That's what's happening. Yeah. All right, is the difference between absolute and conditional convergence clear? Okay. Okay, we already did some examples. So, and here's something that's really weird. So just get ready, okay? This is weird. You ready? If a series is absolutely convergent, then its terms. Okay, so let me just kind of talk out loud here. If something is absolutely convergent, okay, yeah. Okay, that means that if I take the absolute value of the terms, then what? The thing still converges. Make sense? Then it turns out that you can rearrange the terms however you want and like shuffle terms around, and the sum would end up being the same. Okay? Which, I mean, I guess that's not that surprising. Like if I take one plus a half plus, you know, a fourth plus an eighth plus a 16th, right? I mean, you would think, well, what difference should it make whether I add it in that order or if I like shuffle things around into a different order, okay? It turns out that in absolutely convergent series, if I rearrange the terms, I get the exact same sum, okay? However, if a series is conditionally convergent, something weird happens. What's essentially going on, so conditionally convergent means that, right, so what does conditionally convergent mean? We just learned this, but I just want to make sure we're on top of things. That means series AN converges, but what? Series absolute value of AN diverges. So what that means is there's some negative and positive cancellation that's happening. But if I slapped everything to be positive, if I flipped the switch and made everything positive, suddenly I get infinity. Does that make sense? So what has to be happening is the positive terms and the negative terms are both adding up to infinity. And there's just some kind of cancellation that's happening along the way with the partial sums, yeah? And if the positive terms and the negative terms are adding up to infinity, then I am telling you, you can rearrange the terms to add to anything that you want. So somebody give me, so again, I don't want to go into the details here because it gets really weird philosophically and also mathematically, okay? But essentially a conditionally convergent series has positive terms that add up to what? Infinity. And negative terms that add up to negative infinity. That's what has to be happening. Because when I flip everything to positive, guess what happens? I get infinity. Does that make sense? The only way that could happen is if the positive and negative terms both individually add up to positive and negative infinity. Yeah? Now give me your favorite number. 0. Okay? If I have a conditionally convergent series, how could I rearrange the terms to get it to add up to 0? Well, here's how. I take just enough positive terms to get above 0. Stop. Then I take just enough negative terms to get below 0. Stop. Then I just take just enough positive terms to get above 0 again. Stop. Then just enough more negative terms to get below 0. Stop. How do I know I'm never going to run out of positive and negative terms to get me above and below 0? Because the positive terms add up to positive infinity and the negative terms add up to negative infinity. Do you see what I'm saying? So that means you can rearrange a conditionally convergent series to add up to anything that you want. So the order of the terms is actually very important for a conditionally convergent series. Okay? I can even, and this is weird, I can even make a conditionally convergent series add up to plus infinity. How? Well, just keep adding the positive terms and don't ever introduce any of the negative terms. Does that make sense? I just keep adding the positive terms. You know those have to add up to infinity. Okay, and then you just never get to the negative terms. Similarly, I can get it to add up to negative infinity by adding just the negative terms and ignoring the positive terms. So conditionally convergent series are weird. You can get them to add up to anything you want. I mean, look, 57. What would I do to get my conditionally convergent series to add up to 57? Yeah, Michael, you were just above 57? Yeah, then you add some negative terms to get below, positive terms to get just above, negative terms to get just below. You're never going to run out of enough positive and negative terms because after all, the positive terms add to infinity, the negative terms add to negative infinity. Yeah. So I can make the thing arrange, I can arrange the thing to add up to whatever I want. That's bizarre. Okay? But it is absolutely true. So the order of the terms in a conditionally convergent series is critical. But the order of the terms in an absolutely convergent series is not critical. You can arrange those however you want. And you're going to get the same thing every time. Okay? So I kind of gave a verbal example, but you see what I mean. It starts to get kind of technical if you wanted to actually rigorously verify that this was the case. But hopefully we kind of have the idea in our minds. Okay? Any questions on that? Okay, one more thing I want to talk about. I want to talk about remainders. Okay, I want to talk about the remainder for an alternating series. So you might say to yourself, what does the alternating series add up to? Well, it turns out that if you kind of think about the situation, that so by the way, in this little so the remainder is just how far away you are from the total sum. R sub n is how far away you are from the sum, the total sum, with your current partial sum, S sub n. Yeah? And it turns out that you can show, oh, and by the way, we're also assuming this to be the case. What am I assuming about the terms at this point for this alternating series? That they're decreasing in magnitude, okay? Ignoring the alternation, just look at the terms themselves, they're decreasing. Then it turns out that the The error, how far are you off from the sum itself, is just no more than the next term. Okay? So for instance, we're not going to do this, but I just want to do an example. Okay? So what about the alternating harmonic series? Okay, so like S capital N, which is like 1 minus a half. You know this converges, right? Plus a third minus a fourth, plus dot, 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 plus, -1. I think it's to the n plus 1 times 1 over n. That's the nth partial sum. Okay. Actually, the nth partial sum, the nth partial sum wouldn't have a plus 1 in it. It would be, weirdly, it would be n minus 1 here. Right, because I want n total terms, and I actually have a 1 over 1 sitting right here. Oh, wait, I guess it would be n, sorry. Okay, sorry about that. Fix that. Okay, so how far away is this? So the question is, how far away is Sn from S, which is the whole sum? Sum n going from 1 to infinity, minus 1 to the n plus 1 all over little n. How far away is it from this? And the answer that this little remainder theorem is saying is it's no more than the next term. Does that make sense? So Sn, S capital N minus the whole sum is no more than the next term. What is the next term? 1 over, right? It's a sub capital N plus 1, but what's a sub capital N plus 1 in this case? 1 over n plus 1. Does that make sense? Okay, so if I take the billionth partial sum of the alternating series, the billionth partial sum, how far away is that from the total sum? Like how far off am I from the total sum? 1 over a billion and 1. That's the amount of potential error that I might have. Does that make sense? 1 over a billion and 1. So if I take the billionth partial sum for the alternating harmonic, it is 1 over a billion and 1 away from the total sum. Okay, at most. That's what this is saying. Okay, so that gives you a way to kind of approximate how far away you are, and that's important for computers because a computer can then predict how far away am I from the true sum of this series. Yes. And this remainder stuff is important to that end. Okay. All right. Any questions on that? So yeah, let me just write. So S sub capital. I don't know. Let's see. Let's just write S sub. 99. So the 99th partial sum. How far is that away from the total sum? Well, no more than what? 1 over 99 plus 1, which is 1 over 100. Okay, so the 99th partial sum will be accurate to the hundredths position. At least to the hundredths position. Does that make sense? So it won't be off by that much from the true sum itself. Okay, so that's good. Yeah, I think that's all I wanted to say about this. Any questions? Any questions at all? Okay, so we do have some people online right now. So I do want to articulate what I'm going to expect you to do. I'm going to let you work for 20 minutes on this thing. And at the end of those 20 minutes, I'm going to ask the people that are on the internet to kind of do a screen capture, okay? Or hold up their piece of paper to the screen, and then I'll do a screen capture. So here's the problem. It's just a couple of limits that I want you to compute. There they are right there. Can you see them? Okay, so if you don't have a camera, Andrew, you're going to have to, do you have a phone? Okay, so what I would expect you to do is to take a picture with your phone and send it to me via email. Does that make sense? You do that? So we can do it that way. So just these two limits, that's it. As a matter of fact, just give me a second. I'll fix this so that it's not so weird right now, okay? There we go. In fact, if you guys online, if you want to just snap a pic with your phone and then and email it, that's fine.